Welcome back, everybody, for another deep dive. This time, we're going to be tackling entanglement swapping.
Oh, wow.
It sounds a little bit like Star Trek.
Yeah, it does a little bit.
But it is a real phenomenon,
Yeah.
and it has the potential to completely revolutionize so many different things, from communications to computing.
Absolutely.
So to guide us on this journey, we have this essay by Jürgen Schneeppert, and it's
A great essay.
a wild ride, I gotta say.
It is. It really stretches the imagination and makes you sort of reconsider, your basic assumptions about how the world works, how the universe works.
Yeah, absolutely. And, one of the things that really struck me right off the bat was how Schneeppert traces the origins of entanglement, back to Einstein.
Right.
And it all starts with this EPR paradox, right?
Yes.
So Einstein used this thought experiment to kind of challenge the foundations of quantum mechanics.
He did. And he, along with Podolsky and Rosen, they argued that the idea of these particles influencing each other instantaneously over vast distances, what he called spooky action at a distance couldn't possibly be true.
Right.
They thought there had to be some hidden variables that we weren't accounting for,
Mm-hmm.
It was an underlying mechanism that would sort of preserve locality.
So they were basically saying that quantum mechanics was incomplete.
Exactly.
There's more to the story.
Yeah, there's got to be more to the story.
Right.
And Schneeppert does a really good job of explaining how later experiments, like the ones by Elaine Aspect, actually proved Einstein wrong on this point.
So it's not just theoretical anymore.
No.
Like, we actually have evidence that this spooky action at a distance is real.
We do those history. Those experiments showed that the correlations between entangled particles were stronger than any classical theory could predict.
No.
So there's no hidden variable explanation. Quantum mechanics with its inherent non-locality appears to be the correct description of reality.
Okay, so before we get too far ahead of ourselves, can we back up just a little bit?
Sure.
For those of us who are not quantum physicists,
All right.
what exactly is entanglement?
Okay, so imagine you have two particles, let's say photons, that are linked together in a special way, and their fates are intertwined, even if they're physically separated by, a large distance.
Okay.
And we call this entanglement.
Got it.
Now, one of the fascinating properties of these entangled photons is their polarization,
Okay.
which refers to the direction that their light waves vibrate.
So I'm trying to picture this. Is it kind of like a coin flip, like heads or tails, but with light?
That's a good starting point.
Okay.
But it's important to remember that polarization isn't just limited to two states.
Okay.
Unlike a coin, a photon can be polarized in any direction.
Uh-huh.
But the key takeaway is that when you measure the polarization of one of these entangled photons, you instantly know the polarization of the other one, no matter how far apart they are.
So it's not that one photon is sending a signal to the other. It's more like they're sharing some kind of invisible connection.
That's the mind-boggling part. It's a correlation that exists outside of, our usual understanding of space and time.
Right.
And it's so strong that it can even be represented mathematically.
Okay.
Schneeppert emphasizes that you can't describe this entangled state by looking at the individual photons they exist as a single unified system.
That's where my brain starts to melt a little bit.
Yeah.
But how do we know for sure this isn't just some weird coincidence?
Right.
How can we rule out, any other explanation for this seemingly impossible connection?
Well, that's where Bell's inequalities come in.
Okay.
These mathematical expressions were developed to test whether the correlations that we see in these entangled particles could be explained by any classical local theory, one where influences can't travel faster than light.
Right.
And the experimental results, they overwhelmingly favor quantum mechanics, confirming that this spooky action at a distance is real.
Yeah.
And can't be explained away by any classical model.
That's incredible.
Yeah.
So if we accept that entanglement is this real non-local phenomenon, how does that lead us to this idea of entanglement swapping that Schneeppert writes about?
Right.
What makes that possible?
Yeah, that's a great question.
So I think I'm starting to get entanglement, but how do we go from two entangled particles to this idea of entanglement swapping?
Right.
Schneeppert says we can actually create entanglement between particles that have never even interacted before.
Yeah.
How is that even possible?
Well, it's a really kind of brilliant concept, and Schneeppert uses this really clever analogy to illustrate it.
Okay.
Imagine you have two pairs of dancers, right?
Okay.
So if you have one partner from each pair switch, you suddenly have new dance partners.
Okay.
New entangled pairs, even though those new partners never danced together before.
Oh, so it's like a square dance, but for particles.
Exactly.
We're just rearranging the partnership.
You got it.
Okay.
And This partner switching happens through a special type of measurement called a Bell measurement. Essentially, we're not directly entangling these new pairs.
Right.
We're kind of manipulating their existing entanglement to forge these new connections.
It's kind of like introducing two friends through a mutual acquaintance.
Exactly.
And suddenly they have this connection even though they've never met before.
Yeah, that's a great analogy.
But why should our listener care about this?
Right.
What are the real-world implications of being able to swap entanglement around like this?
Well, one of the most exciting prospects is the potential for building a quantum internet.
Okay.
Entanglement swapping is really the key to creating quantum repeaters, which are essential for transmitting quantum information over very long distances.
So it's like a signal booster for entanglement.
Yeah, exactly.
I remember Schneppat mentioning that, even with fiber optic cables, light signals degrade over long distances.
That's right. And a quantum repeater powered by entanglement swapping could refresh that signal, allowing us to transmit quantum information, across vast distances.
Okay, so what would a quantum internet even look like?
Right.
What would it enable?
Well, imagine a world where communication is not only faster, but also completely unhackable.
Oh, wow.
A world where, sensitive data like financial transactions or medical records could be transmitted with absolute security.
Right.
Because any attempt to intercept that information would disrupt the entanglement, essentially destroying the message.
It sounds incredible. It would be a game changer for security and privacy.
Absolutely.
Schneppat also talks about the potential of entanglement swapping for quantum computing.
Right.
Can you explain that connection for us?
Sure. So quantum computers are still in their early stages, but they hold the promise of revolutionizing fields like medicine and materials, science, and artificial intelligence.
Okay.
And entanglement swapping could be really crucial to their development by enabling the creation of these massive distributed quantum computers.
So instead of trying to cram all those quantum bits or qubits into one physical location, we could link individual quantum processors together.
Exactly.
Over long distances using entanglement swapping.
Precisely. It would be like creating a network of entangled qubits, a kind of quantum internet for computation.
And the potential computing power would be just mind-boggling.
Absolutely.
Could you give us a sense of the types of problems that such a network could tackle?
Well, with that kind of processing power, we could finally simulate complex molecules to design, new drugs and materials.
Oh, wow.
We could crack the encryption codes that protect our online data and develop entirely new forms of artificial intelligence.
Okay.
Problems that are simply impossible for our current classical computers to solve.
That's really amazing to think about, but Schneppat doesn't stop there.
He doesn't.
He also discusses the potential of entanglement swapping for something called quantum sensing.
Right.
What is that exactly?
Well, quantum sensing is all about harnessing the strangeness of quantum mechanics to create these hypersensitive instruments.
Hypersensitive in what way? What could they detect?
Well, they could potentially measure tiny variations in gravity or magnetic fields with just incredible precision.
Wow.
Opening up all kinds of new possibilities in fields like navigation and metrology and even, our understanding of the universe itself.
So we've got unhackable communication, super-powered computers.
Yeah.
And incredibly precise sensors.
It's amazing.
All thanks to this bizarre phenomenon of entanglement swapping.
Right.
It's like something straight out of science fiction.
It is.
But Schneppat also reminds us that, this isn't all just theoretical.
Right.
There are real-world challenges to overcome.
Absolutely. He highlights issues like signal loss in optical fibers and the need for highly efficient quantum operations.
Right.
These are engineering challenges that brilliant minds are actively working on.
Yeah.
But then there are, the deeper, more philosophical questions that entanglement swapping raises.
What do you mean?
Well, if we can entangle particles across vast distances, what does that tell us about the true nature of space and time?
Right.
What does it imply about the interconnectedness of everything in the universe?
Yeah.
And perhaps most importantly, what does it tell us about the limits of our own perception and understanding?
Yeah, it seems like every time we answer a question about entanglement, like 10 more pop up.
No, it's true.
This deep dive has really taken us on a journey.
It has.
From the very basics to the truly mind-bending.
It's really a testament to how profoundly entanglement challenges, our classical intuitions about the universe.
Yeah.
Schneepat, does a great job of laying out the historical context and the experimental evidence and the potential applications.
Mm-hmm.
But as you said, it opens up this whole other realm of questions about the nature of reality itself.
And those questions are just as important as the practical applications, right?
Absolutely.
I mean, we've talked about unhackable communication and superpowered computers and hypersensitive sensors,
Right.
which are all incredible.
Yeah.
But entanglement also seems to be pointing us towards something much deeper.
I completely agree. And Schneepat, touches on this toward the end of his essay.
Yeah.
And it's what makes this topic so captivating.
Yeah.
If we can entangle particles across vast distances, what does that suggest about the fundamental fabric of the cosmos?
Right.
Could there be this deeper level of interconnectedness that we're only just beginning to glimpse?
It's as if entanglement is a crack in the surface of, our everyday reality.
Yeah.
A hint that there's something more going on beneath the surface, something beyond our current understanding of space and time.
Exactly. And this is where you, our listener, come in.
Okay.
By engaging with these ideas and asking your own questions and staying curious, you become a part of this scientific exploration.
So it's not just about the scientists in their labs.
Not at all.
Yeah.
It's about all of us expanding, our understanding of the universe and our place within it.
Right.
Who knows? Maybe one of you listening will be inspired to make, the next breakthrough in this field.
Maybe one of our listeners will unlock the secrets of entanglement and finally figure out how to build that teleportation device.
That would be something.
I know, right?
But in all seriousness, the future of quantum technology and our understanding of reality itself is being shaped right now.
Yeah.
And that's a pretty amazing thought.
It really is. So to wrap up this deep dive into entanglement swapping, I want to leave you with this question to ponder.
Okay.
If we can entangle particles across vast distances, does that mean everything in the universe is ultimately connected on some fundamental level? What are the implications of that interconnectedness? And what might it tell us about the mysteries that still lie hidden within the quantum realm?
Those are profound questions and ones that we'll continue to explore.
Yeah.
The journey into the quantum world is just beginning.
Mm-hmm.
And entanglement swapping is one of the most intriguing paths we can follow.
Well said. Until next time. Keep exploring, keep questioning, and keep diving deep